Hello, my friends. Hello, my RF and microwave design engineers, graduate students. Welcome back to my series on ferrite isolator and circulator designs, both microstrip and strip lines. Last session, I have covered the overview of the principle of ferrite isolators and circulators and their application. And I introduced two different designs that I will be presenting. Both designs are designed theoretically first and then are implemented into the 3D modeling tool from ANSYS HFSS. And so today I'm going to continue on for the second part of the series, which will introduce in particular, the strip line. We're going to, microstrip line isolator first, and then we move on to the strip line. And the differences are basically really simple. The strip line, the microstrip line isolator is basically a planar package on a substrate that includes a ferrite material and the magnet, and a surface mount. It drops into a cutout in the board and solders to the three terminals to the board, and you're done. Where the strip line really is encapsulated, it has two magnets and two ferrites, and so it's a little bit different architecture. So last time, let's just put a review. We've introduced the idea of how the principle of operation of the ferrite circulators, how when they're terminated for the reflected waves here, we call it an isolator. Okay, and we've covered that. We have four different types that we're dealing with. One is connectorized circulators, where the ports are basically some of the standard connectors. Like in this case, this one here is SMA. For higher power ones, you might get N-type connectors. And then we have the waveguide, okay, which is basically a Y junction, like as you see with the magnet in here. Of course, the ferrite is sitting inside. And I will probably in the future do a presentation on a design of a waveguide circulator. In fact, it's much easier to do that one than to do these ones. So my interest is basically in surface mount technology parts. So we're going to look at two parts. One of them is a drop-in strip line circulator, and the other one is the microstrip line microstrip circulator. And basically the differences, as you can see here, one is encapsulated, where you got the Y junction is basically suspended either in air or in some kind of material, but it's suspended between two ferrite discs, and the magnets are on top and the bottom, and you won't see them in here. But in a moment, I will show you a tear down circulator where you will see these parts. So, but in both cases, basically, it sits on the surface of a PCB assembly, where the ports get soldered to the corresponding ports. We have covered the applications last time of isolators and circulators, where they fit into the systems, and basically in transceivers, power amplifiers, that sort of a thing, okay? And I have showed some examples of, just grabbed some off the net, some boards that clearly shows a circulator usage on the board, like in this case, and as a microstrip line, like in this case, okay? So let's cover the microstrip one. So we're going to skip over to the strip line to do that on the next series. But before we do that, let's look at the tear down one isolator. This is an isolator because, as you can see, it's a 2-port device. The third port in here is internally connected to a 50 ohm line. So it is really a circulator, but internally it's terminated. And basically that, when we open this, what you see in here, you see a permanent magnet that is embedded in the cover, okay, the top and the bottom. And you see the disc, the Ferrite disc, 2 Ferrite discs, and between the, here's the Ferrite discs, 2 of them right here. And you can see the Y junction, the Y strip line junction is suspended and sandwiched between the 2 ferrites and glued together. And in fact, you can see the glue right here. Look at the glue right here. So you can see that this disc with the Y junction, it becomes a strip line once it's sandwiched between 2 Ferrite discs. And of course, the cover lid and the bottom lid is what is really the ground. So in essence, it becomes a strip line where you have the transmission line, and then you have two corresponding medias up on top and in the bottom. Okay, and here are the magnets once you slip them out of the housing. That's what they look like. That's another example in here, and you can see it clearly. That's another example. It's a little different than this junction in here. So we've got the Y junction in here, and you've got a little bit of a transmission line in here, a step in the width, and that basically has to do with the fact that the impedance of the transmission line is different on the ferrite when you have a ferrite medium, and it becomes extremely it's much larger than the other one. And the other one in here, this is extends from the pin, the center pin of the connector to the strip line. This one here is really a strip line suspended in air. So that's why you see it's very tiny, is because it's divided by square root of 1 instead of being divided by the square root of the medium or multiplied by that. So it's a little different, but in essence, what you really need to do is that what happens is you have the disc in here, you have the impedance at this plane reference in here, and you have 50 ohm in here. So what you need to do, just, you know, simple student level type circuit designs where you have to insert a quarter wave line to do the impedance matching between these 2 ports, assuming they're fully resistive, okay? So let's go to the microstrip line. Now, last session, I showed you the an example design that I did, which is this one here. So we're going to get back to this in a moment. And this was designed for 8.5 gigahertz. Okay, between 8 and 9 gigahertz in here. So this is the frequency response, and here's the return loss and the isolation. So we're going to go over this, and we're going to look at all the corresponding parts. But let's go back and just show what are these pieces. So here's a diagram that shows you a typical microstrip ferrite isolator, which is based on the fact that you have basically it's this part here, but you can see the portion. So we've got a substrate, a BCB substrate, where you make a hole in here with a radius that is equal to the radius of the ferrite material. And the height of the substrate is the height of the ferrite. So you're talking, you know, tens of mils. Now, what I will do when you're designing this, as I will show you in a minute in the HFSS, you can vary the height of the ferrite and see what the impact does, okay? And the idea is that the radius of the ferrite and the radius of the copper disc here, or the brass disc, it really determines the resonance frequency of this. So we've got the equations, and the equations are all based, the design equations are based on equations that were derived by Bosma. It's a very famous name in this field. He was one of the first ones that analyzed electromagnetic physics of Ferrite circulators in 1964, and he derived a set of equations that relates the operating frequency of the circulator to the dimensions of the circulator. And these dimensions are basically the diameter of the cavity in here that is made up of the disk that sits into the Y junction and this. So looking at this, what you have a BCB basically with a hole in there where the circulator drops in, okay? And the circulator basically is, as you can see, here's the copper piece in here, and here's the ferrite. It goes in here, and there's the ground plane in here and underneath, okay? Now, in some cases, you may not find a ground plane of the BCB. Maybe there's a cutout for the whole thing, and this whole thing comes in and drops in. In that case, you would find there is the bottom of the housing, which is metal, basically. So it's the same thing. And of course, the magnet, as you can see, there's a magnet in here. And what we do with the magnet is we glue it using foam disc spacer on top of the ferrite material, okay? So the idea is that now giving us a frequency, operating frequency range, the way to design this is there's a set of equations where at the end, what you're gonna come out with is the diameter of this disk, of the ferrite disk, the height. Of course, you pick the material, and the material now, the thickness of the material is limited really by the vendors. For instance, you go to Rogers and you grab one of the substrates. Let's say the one I'm using right now is Rogers 4003, which is appropriate for, say, X-band, KA, KU band circuit boards. You can see that the thickness in here, you're literally limited to, like, say, anywhere between 8 mils to 80 mils or 60 mils or so, okay? So you can't go very thick on this. You would have to use some other technology to do the thickness of this. Okay, so let's go further on this. So again, just showing you another variant. Sometimes you get some companies, what they do, like this is from Track Microwaves, I guess. What they do, for instance, in here, instead of being at 120 degrees apart, they can do it so they have a microstrip bend included so that you get an alignment between the 1 and 3 ports, and that's just make it easier for circuit board designs. Again, the corresponding diagram in here shows you how basically the construction, the vertical details of this thing. So we're starting out, here's a permanent magnet on top. There's a spacer, it's not shown in here, but there is a Y junction in here that has 3 ports, and the 3 ports have a little step impedance suction to it, because we're trying to do a resistive quarter wavelength matching to the 50 ohm parts. And then we have the ferrite disk, of course, and underneath the ferrite disk, of course, that ferrite disk gets housed into a hole in the substrate material, okay, in the substrate material. And of course, you got the ground reference in the bottom, and that's what it looks like when it's assembled, okay? All right, so now how do we design one of these? And the formulas are basically equal for both strip line and for microstrip line circulators. All it is just switch between the 2 equations, whether it's a microstrip or strip. We start out with the work of Bosma in 1964 in a paper, famous paper that's called On Strip Line Y Circulation at UHF, okay? And this is an IEEE publication. You will see that most of the work that is published on the design methodology of strip line and microstrip lines is basically referenced. It builds upon this facts, okay? And of course, now, these equations really are not the final dimensions of the parts for the circular and isolator. These are a starting point. It's very unlikely that what you're going to calculate out of this is what you're going to get, okay? And so these equations, they're very tedious. I mean, we're not here to do some practicing math, electromagnetic math of Maxwell's equations and Green's function and solving the E field and the H field equations and the isolator circulator as a function of frequency to analyze this. But that's for you. If you're interested, you can go back to these papers. We're merely interested in basically designing and fabricating and sending to production a device. So we start out with basically start out with strip line or microstrip. Y-junction circular design is generally based on the works of Bosma in '64. That's even before I was born. And then, of course, now the initial papers, if you look at them during the '70s, '80s, a lot of them include computer listing of programs and Fortran and BASIC. And what I did for myself is that these equations, you need to program them into MATLAB to really get the calculations. I mean, I would suggest you would, although they are very simple equations, but still to get more accurate, you really want to go to the original lengthy equations where you can actually do some kind of tedious mathematical derivations of the dimensions. When I say dimensions of the circulator, which are basically the diameter of the Y-junction, the width of the line, the length of the line, the diameter of the ferrite material, the size of the magnet, the height of the ferrite, and so forth, okay? Okay, so in a moment, I'll show you the equations. Basically, it turns out, I mean, all you need to do is like 3 simple math equations, and you can get a starting point of a circular design. So the next thing we want to say here is the methods allows the determination of an approximate dimensions of the circular, which is basically what I mentioned, the parameters I mentioned, you know, the diameter and width of the stripline junction, diameter and height of the ferrite, and so forth. And then the fabrication is costly. Now, during Bosma times, the way they used to do these things is they would solve for these parameters and go into the machine shops and machine these parts, and then they would measure it, and then they would go back and change until they get several iterations to get to the final design. Now, luckily, nowadays, we don't do that usually. That's very expensive and very costly, and it's time consuming. And that's what I say here. So luckily now, of course, we have ANSYS HFSS, which made life easy. You can construct these things like I did here, where you can actually you know, sweep all these parameters and even parameterize it. So you end up with all the dimensions are basically programmed as variables in here, sitting with an initial values, and you can actually go in and sweep like I would do here, sweep these dimensions for any of these. So let's say, for instance, I want to sweep the radius of the ferrite material. So I grab that and I say, sweep it and tune. And right now, of course, it's 4 millimeter. So when I will sweep between 2 and 6 millimeters with a step of 0.4, okay? And then you can run it, and it will give you a whole bunch of analysis that you can look in there and see where should the optimal values be at. You could even go further and do optimization. You could go in and set conditions. You want it to have S11 and S12 between this frequency and that frequency, with the return loss below this value, the insertion loss about not more than this value, and so on. And it will go in and solve that for you. Okay, so of course the disadvantage of the classical techniques is that what we do here is we use the 3D modeling to actually come up with the final answers. So just so from this article in here, what we could get basically is the first initial values, which are basically the radius of the disk, the radius of the ferrite, they're equal in this case, okay? And then we can get the length of the feed line in here. Now remember, this copper here sits on ferrite media on top of a ground, okay? Where the feed lines actually sit suspended in air or sometimes on a substrate. In the stripline case, they're really suspended in air. You could put in another substrate in another medium to hold the other ones, but the underneath this is basically the magnet, okay? And the equations are right here, very simple, okay? We've got the radius of the copper and the ferrite is given by this equation, okay? And it's just basically based on the speed of light, the operating frequency, and the magnetic and electrical properties of the material, which are the ferrite permeability and permeability. Okay, and there's a condition that I use. There's another equation that you can actually find the width, but what I did is there's another condition that people have set in where the width has to be 75%, less than 75% of the radius. And I did use that. I didn't want to use the length, another lengthy equation. So what I did is I used that here as my second equation to determine the width of this line, okay? And of course, in the case when you have a substrate in there, that's easily. So you just go into Wheeler's equation and you can find out what the width has to be, okay? And of course, the length in here is a quarter wavelength, okay? So let's go now and basically look at this design here. So how do we construct this? The first thing I would construct, first of all, there is a magnet in here. There's a magnet. The magnet itself is really right now, what I do is it's a non-model object, meaning that it doesn't have any electrical or magnetic properties. So it's not there, but I had it there as physical, just for just illustration purposes, because it makes me remember that there is a magnet in there. But basically what we have, the important thing is that we have a substrate, okay? This substrate is this here, okay, with a hole made that has a that basically we drop into it the ferromaterial disk, okay, and on top of the ferrite disk in here is the printed copper, basically the disk, the metal disk, these things, the copper work. So we've got basically there's a strip line here, a microstrip line here, and there's a disk. Okay, so basically that's what I have right here. Okay, and the way you do this is easily done in HFSS. So you just create one line with a certain width and dimensions. Okay, and all you need to do is just basically after that is you just copy that, duplicate it around the z-axis, okay? Because I've got the z-axis in here out of the page. And so what I'm going to do is rotate this 3 times or 2 times, okay? And that's what's done in here. So we duplicate it 3 times, okay, at 120 degrees apart. And it creates that object for me. So that's how you basically would create the this one, and this one. And that's why I kept them right now. I didn't unify the copper, okay? So let me, just for the sake of illustration, let me hide the medium. Okay, so this is the magnet in here. I'm going to hide it. So this is what we have right now. So we have the 3 lines, okay, coming in and the disk, and these are all unified. I kept them separate so that I could, because they're parameterized, I could go in and say, I want to go to the line here, line here, line here, and the disk, and unify them. Okay, so we could Boolean unite, okay, and they will become one part. But then you really lose the ability to play around with the length of that line and the width of that line. So now, because it became one entity, basically, okay, it's this. So let's get back and just delete that. Okay, let me just, that's the top, I guess that's this. Okay, so we're gonna get rid of these here because it creates them as being non-models. Okay, so, oops. Okay. All right, so let's, so when you, the other, when we, after that, then let's hide this for a moment. So basically what I have right now is I have the, you can see where the ferrite material right here is sitting on top of a ground plane. That's the BCB back, which is metal, basically copper. And then of course, now just the way the simulation of to get the magnet working in there to present the field to the ferrite, what you need to do really is excite this ferrite with a magnetic bias, okay? And that magnetic bias is basically, it really has to do with this material in here, and that's those basically is what has a big factor in the determination of the material. The ferromagnetic material is picked so that these parameters in here determine the frequency, okay? And so the material of this disk here is basically right now is, you can, let's look at it. Let's look at it. It's in the HFSS library, and you can see here are the parameters. So the relative permittivity is 15.1. This material has these magnetic saturation level, the dielectric loss tangent, bulk conductivity, and then the relative permeability, okay, with a pH curve in it, okay? And the delta H and the Landy factor, okay? All right, so this one here, once you do that, of course, you have to create electrical excitation to this. And the way this is done is I attach these ports, okay? And these are metal blocks, basically, okay? Metal, right now they're copper, but you can put them as aluminum if you want, because eventually that's what you may have. Well, eventually, no, you have, this goes to a circuit connection somewhere, because this is, so. So and when you run this, and that's what I get right here with these parameters. The parameters for this, showed you earlier that for instance, the ferrite radius for this is 4 millimeters right now, okay? 4 times 40, that's 160 mils, okay? The height of the ferrite material is 2 millimeters, okay? The radius of the conductor in the Y junction is basically 2, so it's half of that, okay? And then you've got the length and width of the line, okay? So the width of the line, because this material is Rogers 4003. This material, the substrate, which is here, let me bring that to view. This substrate in here, of course, for 50 ohm at this height, that's what we get the length. So now this really the initial design, okay, these values, okay. So, but there's, like I said earlier, let's just see how we do optimize this. And the way to optimize this is I have a whole set of the same file. What I did is I took it and started varying these sweeping these dimensions, okay? So as an example, this first one in here sweeps the height of the ferrite, okay? And so if you do that, like I said, you need to go to the tool in here and go to the materials that you have. So this one here, as an example, is sweeping the height of the ferrite, which is right now is 2 millimeters, but you vary it between 1 to 3 millimeters by 1/10 of a millimeter. Okay, and when I ran this, basically you end up with a set of curves. Okay, that is like this. Okay, so, and then once you get this, you need to go in, for instance, and see which at those other setting values, which one is this? This is 2.3 millimeter. And so you can take that value and go and substitute, put it in the design, and then go again and optimize the other ones. For instance, I did one where just to see let's see, the radius of the ferrite. That's the first one you really want to start with, because that's what verifies the operating resonance frequency. Okay, and if you look at that, that's basically let's look at the results, and you can see how the resonance frequency, the operating frequency changes. And that's what, at first, to tune it, really, that's what you would need to do. You come in and you pick whatever you want. With the particular settings that I had, this happened to be the best operating one. But really, you would, depending on your case, you might have other frequencies, so you need to go that, and then you work on the other parameters. And you repeat this, of course, until you get the final result. Okay, so for instance, I think I had one in here, which is this one here. Let's see this one. Let's see what we got here. The results on this were, oops, I didn't run it. So I don't want to run it right now because it will take a lot of time to compute, but let's just go back to this one here, the one I have. And let's just show you another one also, another method to troubleshoot this. And a lot of times visually you would want to see okay, so that's this one where the center frequency is about, let's see, is about M7, 8.75 gigahertz, okay? And so the bandwidth of this, you can see that between when the return loss is at least -10, and then on this side, -10 is over here. And you can see between 5 and 6, 5 is, well, that's too much loss, so we're gonna get back. We want to try to, at least, depending on the application that you have, you would want the loss not to exceed, say, 0.5 dB. So -40, -0.48 dB here, M6. M6 is here, 0.9. So we're going to get back somewhere, say, about that level. There, M6, 0.5 dB. So if you look at this, it's between 7.8 to 9.3. So it's about a gigahertz operation. That's what you really get most of the times. And of course, the isolation is in the 20 dBs, 25 dB, 22, 23 dB, that stuff. So that's typically what you get from the ones that you buy in off the shelf. Now, one of the things that is really powerful is you can look at the current density in the metal itself, and even animate that, see how it propagates. Okay, so you can see that right now, port 1, let's see no, let's go to, I just want to see which one is port 1. Port 1 is the one that is fed right here. So you can see 1 and 2 is this one, okay? So in a moment, I will show you what happened. Okay, let's go back to this one. You can see that the current, how it's flowing here, and there's nothing in here. Now let's show you what happens is when the signal is, there are reflections from this port back. Does it go here? Of course it shouldn't, because the magnetic field is clockwise in this case, and therefore the propagation should be this way. And let's do that. So I'm going to go in here and to the fields, change the excitation. And here it is the sources, and I'm going to go to port 2 and excite that and zero this, and this should now, as you can see, here's the input now on this side, and all the signal is going into this port. And there's very little going back here. Okay, of course this is the relative strength of the current ampere meter in this one, normalized, of course, or scaled. Okay, so this is really what you get is basically these very simple equations. And basically all you need to do is just, this is how you construct it, ladies and gentlemen. So it's pretty simple. So again, I thank you for the watch this. Please, if you don't mind, subscribe to my channel so I increase the number of people that are subscribing, so you can get notification of the third part of the series, which will be in the strip line. Strip line is nothing but this one here. So what we covered is this, and that one basically the difference is that you just basically stack a mirror image of what you did with the macrostrip. The macrostrip basically had copper, well, it has the magnet, copper, and then a substrate with an embedded ferrite disk in it, where the strip line is a little bit different. It's this really. So you've got the Y junction in here. Okay, but of course, in my case, I'm designing without an SMA. It's really for surface mount. So we don't have a connector like it is here. So 2 disks in a Y and basically it's suspended in air. And that's what it is. It's this one here. So you got magnet on top, magnet on the bottom, and then the rest of the stuff in between. So again, my name is Dr. Mohamed Nezami. I'm a freelance out of circuit board designer. You could, if you have any outsourcing of designs, my rate is very reasonable. I operate in Jordan, Jerash, very cheaply, not like operations in the United States like I used to, where it's pretty expensive. My rate is $25 an hour. You give me the specifications, you give me the concept, what you want to build, and I work with your engineers, and I remotely, I design the whole thing, and I turn in the bill of material, the board, the PCB, the Gerber files, and I follow you all the way until you test. And I can even, if you need a period of time where I could come in and verify along with your test engineers, the prototype operation, I could do that as well. I hold periodical training seminars on basically HFSS, microwave and RF circuits design and system designs using both the HFSS ANSYS and PSI technology pathways, both the system view and the ADS. And I do my layout all in cadence, so you get to have that as well. Okay, ladies and gentlemen, thank you very much, and hope to see you in the third part of this. Thank you very much. Have a great day.